Well, how do we find derivative functions, especially once functions get more complicated? So when functions get more complicated, then finding derivatives using this limit definition will be harder and harder to do. As the functions get uglier and uglier, it takes more and more algebraic manipulation. We're going to see some shortcuts for finding derivatives later on in this chapter. But before we do that, I want to give you a sense of the types of algebraic manipulations that we're going to be doing behind the scenes. So don't expect a lot of these to be on a test or anything like that. Mostly on the test, we're going to be dealing with the shortcuts. But I did want to look at a couple of functions and find their derivatives using the limit definition. Let's take a look first at the function w of x equals sine of x and ask, how could I find the derivative of w for an arbitrary value of x? So we look at the definition. The derivative of w for an arbitrary value of x is the limit of wx plus h minus wx divided by h. That limit would be equal to, if I plug in x plus h into sine, I simply get sine of x plus h. And if I plug in an x into sine, I would simply get sine of x. Now, once again, we have a situation, whereas if you plug in a value of h equals 0, you get an indeterminate form of 0 over 0. So I have to figure out how to simplify that in some way. And it turns out that what we can do is use an identity for sine of two numbers added together. So there's an identity for sine of x plus h that says if you take sine and add two numbers together, you get a certain trig function or trig expression. That expression that you get is sine of x times cosine of h plus sine of h times cosine of x. That's the entire sine x plus h. So that's a trig expression, a big long trig expression in particular, that replaces this sine of x plus h. So that's a trig identity. Now, what can we do once we have that trig identity? Well, we can group the sine of x piece together with this sine of x piece. And we can create essentially two separate fractions so that with one with our sine x in it and one with our sine h in it. So here's how we do that. We take and say we want sine of x cosine of h minus sine x divided by h as one fraction. And then the other fraction is going to be sine h cosine x, all divided by h. This is going to be hard to see, but we're going to now take this and we're going to algebraically manipulate it again. This first fraction, I'm going to factor out a sine of x. That takes the two sine of x's out and of my numerator, and that creates this sine x times cosine h minus 1 over h. And then in this one, I'm going to think of that as factor out a cosine of x times the expression sine h over h. Now, if you remember the technique of limits, limit as h goes to 0 of this. Because this is a constant, I can just pull that out front. And because this is a constant, I can just pull that out front as well. What happens is you end up with sine of x times the limit of h goes to 0 of this expression, cosine h minus 1 over h. And then you also get plus cosine x times the limit as h goes to 0 of sine h over h. Now, here's where it gets a little bit tricky, I guess. I don't know. If you think about dealing with values here, this is an indeterminate form of 0 over 0. I'm going to quickly do this. So this whole limit there gets eliminated because it turns out that whole limit is simply 0. I'm not going to go through that right now, but this whole limit becomes 0. So you get sine x times 0 plus cosine x. Well, we've actually calculated something like this limit before. We've calculated the sine of 3h and gotten 3. Well, sine of 1h over h turns out to be just 1. So this is just sine times 0 plus cosine times 1, which is equal to cosine of x. Now that's a lot to do, right? So all of this required me to know the exact precise trig identity to use, and then how to precisely split it up, and then how to precisely be able to factor out a sine, but leave the sine of x, but leave the cosine hh in there. And then it also forced me to know this limit. It forced me to know this limit. That's a lot of work, but we did end up figuring out that the derivative of sine is cosine. Now, if I ever want to go back and figure out derivatives of sines at various values of x, I can simply plug it in to my cosine function. So what's the derivative at 0? Plug in 0 into cosine. What's the derivative at pi? Well, plug in pi into cosine. What's the derivative at pi over 3? Plug in the value at pi over 3. You see the point. It took a long time, but we did end up seeing that the derivative of sine is cosine. Let's take a look at another manipulation example. We are going to find the derivative of r of x, which I call 4 over x. So we take the derivative of 4 over x. This one will be a little bit more straightforward than the previous example. It still is interesting to go through though. So when I plug in x plus h into my function 4 divided by x, I get 4 divided by x plus h. When I plug in x into my function, I get 4 over x. Now, this is a lot of nasty fractions, but we can still deal with it. So in order to deal with ugly fractions, I need to make those simpler. The easiest way to go ahead and do that is to create common denominators. So I'm going to take and create a common denominator on top. X plus h times x is my common denominator. Now, if I want to put both these fractions over common denominator, the first fraction I need to multiply by x on both the top and bottom. The second fraction I need to multiply by x plus h on the top and bottom. Notice what that is going to do. I am going to distribute this 4 in. I'm going to get 4x plus 4h on the top of my second fraction. And then when I combine fractions, what happens is I end up with the 4x minus 4x canceling out and giving me 0 x's. And then a minus 4h gives me a negative 4h on top. So the whole top can be simplified into one big fraction. Negative 4h divided by h plus x times x on the denominator. Let's take a look at this. Well, dividing by h is the same thing as multiplying by 1 over h. So let's multiply times 1 over h instead of dividing by h, just to see how that works. So multiplying times 1 over h gives us another h in the denominator. 4h times 1 in the numerator is just 4h. And notice now I can cancel out this h here with this h here. So what happens is that we end up with negative 4. Doesn't matter if you put the negative out front or in front of the negative, in front of the 4. Negative 4 over x plus h times x. And now this is the first time that I can plug in a 0 into my denominator and not be dividing by 0. Notice if I just plug in a 0 into my denominator, I end up with negative 4 over x plus 0 times x. Or in other words, negative 4 over x squared. And so if my function we called r, then my derivative of r is negative 4 divided by x squared. And now I can find derivatives no matter what the value of x happens to be.